So in the last class, we discussed about risk and CISC. So first of all, I want to confirm from your side. So are you in energetic mode to listen to the class, or simply for the attendance sake you are sitting first? So anyhow, I think some part you have learned from your morning class. So now, in this class, we are going to discuss about the difference between your von Neumann and Harvard architecture of the microprocessor. Okay. So you have already gone through this particular thing. So we are going to just brush it up what according to the syllabus point of view. That's it, nothing else. So now, when you take the difference between your Harvard and von Neumann architecture with respect to the processor architecture design. Okay. So whenever we are going to discuss with respect to the architectural design of any processor, first we should know what are the two different types of architectural design. That is, one is it is going to have von Neumann architecture, other is your Harvard architecture. There are two types of architecture which you are going to have. Okay. So now, if we take the von Neumann architecture, since already you people have known that one. So if we take the von Neumann architecture, so in the von Neumann architecture, what it is going to have, it is going to share a common bus. Okay, it will going to share common bus for fetching both instruction and data. So single bus will be there. So the single bus itself, it has to use to fetch the data as well as the program, okay, or instructions. Okay. So now here, whenever you want to store this particular, since it is using the common bus, so your program instructions and data. So you're going to have the program instructions and data. The program instructions and data are stored in a same memory. Okay, it is going to have the common memory. So are stored in common memory. So that's what your von Neumann architecture is all about to tell. Now, if you take the Harvard architecture, so it's going to have the separate bus, right? So you have gone through, you have seen how the Harvard architecture looks and how the von Neumann architecture looks. So in the Harvard architecture, what will happen? It is going to have the separate bus, okay, separate data bus to access the data, and separate instruction bus to fetch the program. Now, since it is going to have the separate bus to have the instruction access as well as the data access, so the speed, the data transfer will become fast, where in your Harvard architecture. So here you can see that the data can be read and written while the program memory has been accessed. So since it is using the separate bus for the data memory as well as the instruction memory, so since you are going to have two different bus, it's normal, but it is general that if you are traveling from Yelahanka to college, so if you are using two different bus for carrying the girls and carrying the boys, obviously both the people can reach the destination easily. The same way here. So you're going to have the data. So data bus, it is totally different, and the instruction bus is totally different. So from the figure, you can see that this separated data bus and code memory bus allows one instruction to execute while the other instruction is fetching. That means what? So you can have the parallelism. So if you're going to have the Harvard architecture, so you can achieve parallelism. So why? It is going to have the separate bus, because since it is going to have the separate bus, so it will allow one instruction to execute. Okay, so one instruction to execute, and whatever the data it is going to store and manipulate in the memory, while the other bus is going to make use of fetching the data or fetching the next instruction which has to be executed. So those are the two different uh, functionalities where your Harvard and von Neumann architecture is going to have, and advantage of Harvard architecture. So you can see it here. So you're going to have the Harvard program memory as well as the data memory. So here in this one, we have not specified the bus. So just specify the bus here. So it's going to have two-dimensional. So it's going to have the specified bus which is connected here. Okay. So separate bus for data memory, separate bus for program memory. So once the program memory is going to make use of the instruction which has to be executed next, then your data memory is the program will be the instruction will be executing the instruction depending upon the data memory which is available. So by the time when it is executing with respect to the data, so the next instruction can be fetched from the program memory. So that's what is going to happen. Okay, in your Harvard architecture. Whereas in your one human architecture, since it is going to share the common bus, you can see it here. It is going to share the common bus. So one operation can be performed at one instance of time. So since it is only one operation which is performing is going to have performed in one instance of time or at one time. So what is happening? Obviously, the performance will be reduced. Okay, so obviously the performance is going to be reduced. So now if you take the difference between Harvard and one human architecture, in the exam they may ask you that what are the difference between Harvard and one human architecture. So in the Harvard architecture, is going to use the separate buses for instruction as well as the data fetching. Whereas in your one human architecture, it's going to have the single shared bus for instruction and data fetching. So now since it's the Harvard architecture, it is going to make use of the two separate buses. Since it is going to have the separate bus, pipeline can be achieved and it is easier. Okay, so pipeline can be achieved and it is easier. So what do you mean by pipelining? Any answers from your side? What do you mean by pipelining? So pipelining is nothing but you are going to overlap the instructions. Okay, so you are going to overlap the instruction execution. For what purpose you are overlapping the instruction execution? You are overlapping the instruction execution to achieve the performance. Okay, so you are going to overlap the instruction execution to achieve the performance. Now, when you are achieving the performance, obviously the code which you are supposed to run, it will be executing faster. So obviously the performance will be more when it compares to the Harvard architecture. So when it comes to the one human architecture, it's going to have the low performance. Okay, it's going to have the low performance compared to the Harvard architecture. So now when it comes to the Harvard architecture, since you are going to have the separate data bus as well as the address bus. Now, if you are separating the database means what? So one extra additional component you have to have. So obviously, when you are going to have, the cost will become high. So it is going to have the comparatively high cost compared to the one human architecture. It's cheaper. So now you are going to have the Harvard architecture. You are going to have the no memory alignment problems will be there. Since the memory alignment is fixed in your Harvard architecture. So whereas in your one human architecture, it depends upon the code which you are going to use or it depends upon the instructions which you are going to use. Okay. So since data memory and program memory are physically different locations, so now since it is stored in two different memories, so we are going to have no chances of accidental corruption. Okay, accidental corruption of data won't be there in your program memory. So here, since it is going to share the common bus, since the data memory and program memory is going to be shared shared by a common bus, and whatever the memory you are going to use, that particular memory is single only. So that particular memory, both your program memory as well as the data memory will be stored physically in a same chip. So now when you are going to have stored those those data and instruction, data and program in a single chip, there may be a chance of accidental corruption. There may be a chance of accidental corruption of program memory. So that is what the difference between your Harvard and one human architecture. So anybody having any doubt with respect to this between your Harvard and one human architecture? Anybody is having any doubt? You have to speak up. If you don't speak up, so it will become difficult for us to know at what level you are in. Okay.
Suresh,
Yes,
can
sir.
you make that full screen? PT.
Yes, sir.
Okay. Okay. Carry on.
Okay. So now the next topic which you are going to have to be discussed is big endian and little endian processor. So now when it comes to the big endian and little endian processor, we have to see that
Suresh, ಇದು subject code ಏನು?
18CS44, sir.
18CS44. ಇದು ಯಾವ್ದು CO2 ನಾ ಯಾವ್ದು?
ಇದು CO3, sir. ಮಾಡ್ತಾರೆ.
CO3 ನಾ? Okay. CO3. Okay. Thank you.
So now the next part which we need to discuss is big endian and little endian processors or controllers. So now, as we have already discussed with respect to the little endian, big endian in the previous classes, so I think that have been explained in the lab part only how this particular data will be stored inside your memory. So how the data will be organized. So now can you tell me that, as I told you in the lab part, so how many, if you want to store the data, so how many bytes of data will be stored in one memory? How many byte of data is stored in one memory?
1 byte.
1 byte, right? So now when you are going to have the NDNS, so it specifies the order in which the data is stored inside the memory. Okay. So because the data, how it is going to be read. So if I am going with the big NDNS, how the data will be stored in that particular memory. If I go with the little NDNS, how the data will be stored in that particular memory. Okay. So now, so if for the word length more than 1 byte, so the data can be stored in memory in 2 different ways. Okay, as I told you that since the data is stored in one memory locations requires 1 byte of data. So if you are using only 1 byte of data, then there is no issue. If you are using only 1 byte of data, then there is no issue. Okay, so now if you are going to have if you are going to have the data which is more than 1 byte, if you are going to have the data which is more than 1 byte, then there are many ways. There are 2 different ways where the data will be represented. So the data which is going to be represented is in 2 ways. One is little endian way and other is big endian way. Now in the little endian way, how the data will be stored is the first one. So if you take the little endian way, so the data will be stored in such a way that, so the higher order of data byte at the higher memory address. Okay, higher order of data byte, so at the higher memory address, and the lower order of the data byte at the lower memory address. Okay, so you can see that for byte long integer, for example, if you take, so if the for example is for here, it is going to have 32-bit information, that is F0, B0, FF99. Now your 99 is nothing but what? Byte 0. Your FF is byte 1, B0 is byte 2, your F0 is byte 3. Okay, so now when it takes the memory address, if you take the memory address, assume that the memory address which I'm going to have is 2001, 2002, 2003, 2004. So these are the 4 different memory address which you are going to have. So now once you are going to have this particular type of memory address, 2001, 2002, 2003 and 2004. So as the name, as the definition tells for the little endian, so here it will, what will happen? So your lower byte is going to be stored in lower memory address. So here the lower memory address specified is 2001, right? So the lower byte will be stored in 99. So the next byte 1, if you take the byte 1, the next byte 1 will be stored in the next IR address, that is FF. Here in this particular example, it is going to be stored in 2002. So next byte 2, if you take the byte 2, it is going to be stored in 2003, which is the content which has to be stored is B0. So B0 is the content which has to be stored, that will be stored in 2003. And the higher byte, which is F0, it will be stored in higher address. So the higher address is 2004. So now, as I told you that one memory location is going to store 1 byte of data. So now if I want to store more than 1 byte, then it is a problem. Then I have to go with the when I'm going to make use of the architecture with respect to NDNS, how the data will be stored inside that particular processor. So now, if you want to tell, so which are the higher byte, so you can see it here. So as I told you,
It is not visible.
it's visible now. No, right?
Mm.
Power went off. 1 minute. So whether it's visible now?
Yes, sir.
Okay. So okay. So now here you can see that the memory address, if you are considering more than one byte of data. So if you are considering more than one byte of data, so what you are going to have? So you're going to have F0, B0, FF99. So you're going to have 2001, 2002, 2003, 2004. So now you can see that. So byte 0, it is lower. Byte 0 is the lower memory address, the lower byte. 99 is the lower byte. That will be there in the lower memory address. FF is the byte 1. It will be stored in 2002 address. F as B0 is the next byte 2, which will be stored in 2003 address. And your byte 3 is F0, which will be stored in 2004 address. Okay. So anybody having any doubt with little endian now? Anybody having any doubt? Anybody having any doubt?
No, sir.
Okay. So now when it comes to the big endian, it will reverse. So in the big endian, what will happen? So in the little endian, that was different. So this is big endian. Okay. So just I will change the. So this is big endian. Okay. So when it is going to big endian, what will happen is here the higher order data byte at the higher memory address. Okay, the higher order memory, the higher order of data byte at the higher memory address, and the lower order data bytes at the lower memory address. So you are going to have that one. So it will be reverse here. So the higher order data byte at the lower memory address. Okay, this will be lower memory address. That order, it will be reverse as of the big endian. Okay. Okay. This big endian only. So byte 0 will be at byte 0, which is 99 will be at the higher address. Okay. Okay. So you can see it here from this one. So if you are going to have the byte long integer, so here what will happen? The lower byte will be at the higher address. The lower byte will be at the higher address, and higher byte will be at the lower address. The higher byte will be at the lower address. That's what it's going to have. Okay. So in this one, what will happen? Higher order. So just higher order data byte at the lower address. The higher lower order data byte at the higher memory. So just a change you make it. Okay. Now, so if I that one here, you can see it here. So if you take this particular higher order data byte at the lower memory and the lower order of the data byte at the higher memory. So you can see it here. So if you take this particular byte long example, the same example I am taking, which is going to have F0, B0, FF99. So if I'm going to have this particular example, that is 99, FF, B0 and F0. So you can see it here, byte 0, byte 1, byte 2, byte 3. That is 99 is byte 0, FF is byte 1, B0 is byte 2, F0 is byte 3. Now, as the title indicates, your higher order, lower order byte data byte at the higher memory. So that means if you take the 4 bytes to store the data, so to store 4 bytes of data, you require 4 memory location. Okay. So to store 4 bytes of data, you require 4 memory location. Assume that I have to store this particular data in the memory location 2001, 2002, 2003, and 2004. Now, here the higher address is 2004. So in the 2004, I have to store the lower byte. Lower byte is byte 0, which is 99. So next is the next byte 1. That is the byte which is next to the lower byte, which is FF. That will be stored in address 2003. Now B0, it will be stored in byte 2 will be stored in B0, which is byte 2. It will be stored in 2002, and your F0, which is byte 3. F0, which is byte 3, that will be stored in 2001. So this is what how the data will be stored in your big endian. Okay. So anybody having any doubt between little endian and big endian? Sir, if you take the big endian, the example processor for your big endian is FPC 68000, or most of your microprocessor, Motorola processor is big endian only. So now, why it is so like that? So why I have to go with the big endian architecture only? So why we have to go with the big endian architecture only for byte long integer? So anybody having any doubt with respect to little endian and big endian now? In the little endian, lower byte, lower memory address, higher byte, higher memory address. Whereas in big endian, lower byte, higher memory address, higher byte, lower memory address. Anybody having any doubt? Anybody having any doubt? Yes or no? That's it.
No, sir.
Okay. So next is load store operation and instruction pipelining. This we have already discussed. So now most of the RISC architecture, if we take the RISC architecture, RISC processor instructions or the instructions which will mainly operates on the register. Okay, it will mainly operates on the register. Now, when you are going to have the instructions which is operating on the register, here the memory related instructions. The memory related instructions, first it has to be performed using the load and store instructions only. So as I told in your normal ARM processor, ARM is a RISC-based machine. So whenever you want to operate on memory, so what we should have? We should have a knowledge that first the data has to be brought from the memory to the register. So if you are bringing the data from the memory to the register, what operation you are supposed to use? What is the instruction? Which instruction you are going to use if you are bringing the data from the memory location to the register?
Load.
Load. Yeah. Load is the instruction which you are going to use to bring the data from the register to the memory location. And if you want the data to be stored from register to the memory location, you are going to make use of the store instruction. So that's what. So now, whenever you are going to discuss with respect to the RISC architecture, so normally if you take the RISC type of architecture, always the RISC type of architecture is referred as load store architecture. The RISC type of architecture is referred as load store architecture. Okay. So next, if we take the load store architecture here, so this is instruction pipelining. So already we have gone through the instruction pipelining, right? That is, it is going to have how many stages if you are going to make use of ARM7? If you are going to make use of the ARM7, it's going to have 3 stages. That is, one is fetch, decode, and execute. Okay. So now, so you can take this one as a reference. That is instruction 1. It is loading the data from the memory location X into the register R1. So the second instruction, it is loading the data from the memory location Y to the register R2. And the third instruction is going to add the contents of register R1 and R2, and the result which is obtained, that will be stored in R3. That it will be stored in R3. So next you are going to have the instruction which is going to have store R3 comma Z. That means what? In the store instruction, what will happen? The data which you are going to have, that will be moved from the register to the memory location. The data which you are going to have, that will be that you are going to move from the register to the memory location. So now if you are going to have this particular type of scenario, you can see it here. So now in the load store operation, first what the data has to be there. So if you take this particular memory location, so here the X is memory location, the data which is there is 0, 0. First that particular data which is 0, 0 has to be loaded to the register R1. So you can see it here at the registers. So it is the memory location. XYZ is the memory location. Now when you are going to have the XYZ memory location, first the data will from the memory location X is moved to the register R1. So next instruction which is load R2 comma Y. So in this particular instruction, what it will do, it will load the data from the memory location, specify memory location Y, which is 7F, that will be loaded into the register R2. Now, once it is done, the operation add has to be performed. Since it's the arithmetic operation which has to be performed, that will be performed in ALU. That is arithmetic and logic unit. The arithmetic and logic unit is going to perform the third instruction, which is adding of the contents R1 and R2. And the final, whatever the result it will obtain, that will be in the temporary memory at that time. Okay. So now after that one, ALU is going to move that the result will be stored to the register R3. Okay, the result will be stored to the register R3. Next, the data which is there in R3 has to move to which location? Z location. So the flow you can see it here. From R3, the data has to move to the memory location R3, 23, Z. So the Z location, the result will be obtained. So don't look the value. It is just a value which has been specified there, but it's not proper values which are there. Just for your reference, we have taken some values. But if you take what the exact values, that is 7F plus 0 is 7F only, the result which you are going to get. The same 7F will be returned to the memory location Z. So this is how the load store architecture is going to work. So when you talk about the load store architecture, okay, when you start talking about your load store architecture, so you can see it here. So what will happen for this particular instruction pipelining? So if we take the instruction pipelining here, so if we take the instruction pipelining, so in the instruction pipelining, what will happen here is, first is load. So we are loading what content? R1 to X, R1 comma X. Then we are loading the contents of memory location Y to R2. Then we are adding the contents of R1 and R2, and we are storing the result in R3. Next, we are going to store the contents of R3 into Z. Next, we are going to store the contents of R3 into Z. Next, when you are going to have this particular type, so here what will happen here? First, you are going to have fetch and decode. Okay, fetch and decode is the instruction which you are going to have. Now in the fetch and decode, what will happen? So the conventional instruction execution processor follows the fetch, decode, execute. Okay, so that we have already discussed. So fetch. So from where the fetch, the instruction has to be fetched. Who is going to keep track of the instruction? Who is going to keep track of the instruction to be fetched? Can anyone tell? Who is going to keep track of the instruction to be fetched?
Program counter.
Yeah. So the instruction has to be, the program counter is holding the address of the instruction, which has to be fetched next. Now, once this particular instruction is fetched, your program counter where it has to point. So assume that this particular instruction is there in, so that depends upon the type, size of the instruction. So even if we take the load, so load R1 comma X, so this instruction is also converted to, this is machine language instruction. So now this instruction is also converted to machine language. Okay, this instruction is also converted to binary language before executing. So now we are going to have, assume that it is going to have 1 byte instruction, 1 byte or 2 byte instruction. So if you are going to have 2 byte instruction, so the instruction will be of how many, what is the size of the instruction? It will be 2 byte. For example, I'm telling, because different processor manufacturer will tell in different ways. So what should be the size of the instruction? So if it's a 2 byte instruction, how many memory locations it requires to store that particular instruction? If it's a 2 byte, if it's a 2 byte instruction, how many memory location it requires to store that particular instruction?
2 memory.
Yeah, 2 memory location it requires, right? Now, for example, I'm telling at 2000 address, you're going to have load R1 comma X. The next instruction will be stored in 2002. That is your load R2 comma Y. So the next instruction will be stored in 2004 and your add instruction is going to be stored R3 R1 comma R2. So next it is going to store 2006. Then there is going to have the instruction store R3 comma Z. Okay. So now when you have this particular type of instruction, so once this is fetched, so initially what the program counter was 2000. Okay. Once it is fetched, so assume that the fetch instruction has been executed. Now the program counter, what it has to hold down? What is the data it has to hold down next? Once it is fetched already, next instruction to be executed. Which address it has to store now? According to year 2000. No. Which is the next instruction where it is starting? It is 2002. Okay. So it is 2 because I am telling one instruction is going to take 2 bytes of memory. So if it is 2002 bytes of memory, this particular load Rn(x) is going to take 2 bytes. That is, first memory binary will be stored in 2000. The second will be stored in 2001. The next memory instruction is starting at 2002. Your program counter will be incremented by 2. That is 200 plus 2. It will be pointed to this. Now in the next cycle, what will happen? So in the next clock cycle, when it is executing, if you take the instruction 1, this is instruction 2, this is instruction 3 if I take, and instruction 4 if I take. So now when it is executing, what operation here it is going to perform for the instruction 2? What will happen in pipelining? So this will be the fetch stage. This will be the fetch stage. So now once it is fetching the second instruction, where the next program counter has point to, next it has to point to the next address which is located in 2004. Since we are assuming the load R2 comma Y is consuming 2 bytes of memory. It is going to consume 2 bytes of memory. So next, once it is done, fetch, decode, execute, right? It is decode and execute. So when the first instruction is executing, second instruction will be in decode stage. The third instruction will be in execution stage. your instruction 3 will start here. Fetch, decode, execute. So your fourth instruction will start fetch, decode, execute. So if you take this the number of clock cycles, how much it is going to take? So you can see it here: clock cycle 1, clock cycle 2, clock cycle 3, clock cycle 4, clock cycle 5, clock cycle 6. Okay. So now total number of clock cycle to complete all 4 instructions is how much? 6. Total number of clock cycle taken is 6. 6 clock cycle. Now, if it is taking 6 clock cycle, you can see it here. If I'm going with the sequential execution, so total number of clock cycle taken to run one instruction is 3. Total number of instruction is 4. So it will be taking 12 clock cycles. So by implementing pipelining, what I am achieving? By implementing pipelining, by doing pipelining, if there is no dependency, okay, by doing pipelining, it is 12 clock cycle minus 6 clock cycle, which will be, you are going to have the advantage of 6 clock cycle. That means you have reduced the 6 clock cycle. That means you're having the advantage of 6 clock cycles. That is nothing but when you are reducing the clock cycle, obviously the performance will be getting increased. Okay, so that's how you are going to increase the performance by using the pipelining. That you have seen in your microcontroller itself, right? That we have discussed in microcontroller itself. So that again you have to read it. So now the same thing we are going to explain here. The conventional instruction execution by the processor follows the fetch, decode, and execute sequence. So the fetch part, what it is going to fetch? The instruction from program memory or code memory, and decode part decodes the instruction to generate the necessary control signal. And the execution state reads the operand, perform ALU operation, and stores the result. So now, in normal program execution, if we are going to have, so the fetch and decode operations are performed in sequence. Okay, fetch and decode operations are performed in sequence. So during the decode operation, what will happen? The memory address bus is available, and if it's possible to effectively utilize it for instruction fetch, since the memory bus is available during that particular phase, the decode phase. So you are going to have the fetch. So now, what do you mean by instruction pipelining? So instruction pipelining refers to the overlapped execution of instruction. So the same thing you are saying. In the machine cycle 1, what will happen? You are going to fetch the instruction from the program counter. So now, next, it is going to fetch the program counter +1. That is the next clock cycle. And you are going to execute what? Which has been fetched in the previous cycle. It will be executing in the previous cycle. So next it is going to fetch the third instruction, and it will be executed in the previous instruction. So this particular example, what they have given in the textbook is for 2 stage. It is only for fetch and execute. Okay. So we have discussed 3 stage, but the diagram what they have given in your textbook is for 2 stage. That you have to keep in your mind. Don't get confused with respect to the definition what they have given in the textbook and the figure what they have given in the textbook. The figure what they have given in the textbook is with respect to the 2 stages of pipelining. The figure which they have given in the textbook is of 2 stages of pipelining, whereas your figure which they have given is for 2 stage figure. So the explanation is given for fetch, decode, and execute, which is for 3 stage. That you have to overcome that one. So that is about your pipelining and load store architecture, which you are going to make it useful in your RISC architecture. Okay, so that's what the advantage which you are going to have in your RISC-based machines. So next comes application specific integrated circuit. Okay, anybody having any doubt there in pipelining? If you have any doubt with respect to the difference between your Harvard and von Neumann architecture, have you got any difference between your von Neumann and Harvard architecture? Harvard and von Neumann architecture, anybody having any doubt? Or if you have any doubt with respect to the next topic, which we have discussed is little endian and big endian. If anybody having any doubt with respect to little endian and big endian? Yes or no? That's it. Why you people hesitating to tell yes or no? Whether you are bored? Yeah? Okay. So if you have a doubt, you speak up. If you don't speak up, it will become difficult for us to analyze at what level you are in. Okay. So next comes the topic, which is application specific integrated circuit, which is normally called as ASIC. So ASIC stands for 1 minute. No. ಇಲ್ಲ ಇನ್ನೂ ತಗೋತಾ ಇದ್ದೀನಿ ಸರಕ್ಕೆ. ಸರಿ, ಓಕೆ, ಸರಿ, ಓಕೆ. So now, when it comes to the ASIC, that is application specific integrated circuit. So here, application specific integrated circuit, as the name indicates, what it suggests. So that is, you are going to have the IC. Whatever the IC you are going to have, that particular chip is going to perform one application. The one unique application that it's going to be performed. That is nothing but what? So if you want to perform any one of the application, any one application to be performed, or any functionality should be there to perform. So that particular functionality will be specified and it will be stored inside the ROM. So now that is where your firmware designer is going to have the role to play. So all of you know what do you mean by firmware designer? Anybody knows what do you mean by firmware designer? I will continue application specific integrated circuit tomorrow. I want from your side that, do you know that what do you mean by firmware designer? Anybody have the answer for that one? What do you mean by firmware designer? Firmware designer.